Next, we have Pau Mir with the rigidity of cotangent lifts in interval systems. He's Eva's student, I believe. So we'll be continuing on from her talk yesterday.
First of all, I wanted to thank Amna, Manuel de León, and all the organization of ICMAT who invited me here and who have been preparing this congress that ends today and has been really nice up to now. And also to Professor Peter Purchaser, because it was a really interesting talk connecting momentum maps with even deep learning. So for me, it was really interesting. Thank you, Professor Purchaser. And today I will talk about rigidity, about a concept which is quite related with momentum map theory, because there's some polytopes already give some strong kind of notion of rigidity, but I will focus it from another point of view, from the point of view of the cotangent lift, which is a tool which offers another approach to physical problems, and for which we have extended some classical rigidity results from Richard Palais to this cotangent lift setting. I will try to share my screen, and please tell me if you can see it.
Yes, can see it.
Okay, perfect. So today we'll talk about rigidity of group actions at the level of cotangent lifts, and we will see that it has that our results that were joint work with Professor Miranda, who is here, provide applications to integrable systems. So this cotangent lift setting is the natural setting of a lot of integrable systems that come from physical problems, as we will see with some examples. And we will start by the rigidity theorem, which we adapted for the cotangent lift, starting from a foundational result from Richard Palais a long time ago. And we use a result which was also kind of previous than us, which is a result from Eva Miranda from 10 or so years ago, if I'm correct. Yeah. So to start, I will, as I said, talk about this new theorem on rigidity of group actions on the cotangent lift. We will explain what is the cotangent lift, which are the advantages of using the cotangent lift. Then we will see that this theorem has applications in form of other theorems to integrable systems. And then we will see that these applications that deal with systems that have singularities are useful because they can be applied to some real problems which contain singularities. In fact, are mechanical systems which do contain singularities, which is the normal thing. You don't encounter mechanical systems that are regular everywhere, but you find singularities at some points of the mechanical systems. And finally, I will give a very brief overview about the B version, the symplectic version of all our results in which we are working now and which are work in progress. So to start with very basic concepts and things, we use group actions. We talk about movement maps of group actions and Hamiltonian actions, because group actions represent well the change in some aspects of real systems, of real objects that we model with manifolds, with differential manifolds, and in mathematical physics with symplectic manifolds. And symmetries can be modeled with group actions, and if, as you know, the group action is carried out by a group which is also a manifold, we call it a Lie group action, which has this general form. In fact, this image I put here of a Rubik's cube is a group action which is discrete, but you can have group actions like the action I put in the first slide, which is the continuous group action, has the shape of the structure of a map. We will talk today a lot about rigidity, and rigidity is really connected to stability. Stability in geometry is when we call when a property is maintained if the function keeps a property if we perturb it a little bit. So if we construct an homotopy in which all the functions in the homotopy also possess the original property. If a property is maintained and all the functions in the homotopy also possess it, we call that this property, not the function, but the property is stable. For instance, to put a super easy example, this curve that you can see here in the plane has different properties, has a lot of properties, and one of them, for instance, is passing through the origin, and another one of them, for instance, is to intersect transversally the axis. One of them, intersecting transversally the axis, in this case the x-axis, is stable, since you can perturb it a little bit and you will not lose this property. The other one, the contrary, is not stable because passing through the origin is a property that you lose if you perturb this function little. Only if you have you're extremely lucky and you perturb it in the exact direction, you would not lose this property. But in general, after a general small perturbation, you would lose this property of passing through the origin. So this is the basic idea of stability, and stability is connected with rigidity, because you can think of stability and as a remaining the same after a small perturbation. And we think about rigidity of actions, group actions, as a stability in another formulation. We say that an action is rigid when nearby actions are equivalent to it. And you can think that nearby actions are the original action which has been perturbed with a small perturbation. So more or less are the same concept about stability and rigidity, is that you possess some properties, and these properties are kept when you take an action which is really close or when you perturb the original action little. So this is the basic concepts we will deal with in this presentation. The foundational rigidity result on group actions is a theorem by Richard Palais in the 60s, in which he proved that two compact Lie group actions, so two Lie group actions of a compact Lie group, acting on a compact manifold, if they are C1 close enough, they are equivalent. This C1 close means that they are close in the C1 topology, in the usual topology of opens of continuity, open continuous topology. And by equivalent, Richard Palais meant that there exists a diffeomorphism that conjugates both actions. So if you have two actions, in this case, row 0 and row 1, if they are C1 close enough, then you can find this diffeomorphism phi that conjugates both actions. So they are equivalent. They possess essentially the same properties. This result was improved by Professor Miranda here in 2007 in a symplectic version, in a symplectically equivariant version, because the result of Richard Palais was in general manifolds, in general differential manifolds, but in this theorem, Miranda proved that you can construct, if you have this compact Lie group action acting on a compact symplectic manifold, then you can find that this diffeomorphism that conjugates both actions is not only a diffeomorphism, but is a simplex homomorphism. So these two actions are conjugated by a simplex homomorphism. So they are not only equivalent, but simplexically equivalent. The only detail is that you have to require more than Richard Palais requires in his theorem. You have to require that they are C2 close, because in the proof, you need to differentiate 2 times instead of 1. This is what connects with momentum map theory, momentum polytope theory, because in case of toric actions, if this action of a Lie group was toric, you already know that this action is rigid, because the León theorem, which provides this León polytope, already provides rigidity of the general polytope, of the points on the polytope, especially of the singularities that you have in the polytope, all the kinds of non-degenerate basic singularities. But this is kind of a more general situation, because here you don't require, in this theorem, it does not require that the action is toric. So this goes a little further than the advanced classical theorem in the aspect of rigidity, not in other aspects. So I already spoiled you that we will talk about the version of this theorem, which is in the cotangent leaf. So we'll introduce what's the cotangent leaf of a Lie group action. First, we have to set ourselves in the cotangent bundle, which is the natural bundle to formulate physical problems. And in the cotangent bundle, you all know that there is a canonical one form, the Liouville one form, which in local coordinates, and you can always writes as PDQ. And the nice property it has is that its differential is the symplectic form in the cotangent bundle. So every cotangent bundle is a symplectic manifold, since you can always find a symplectic form there, which is a differential of the Liouville one form that you always have there. And in the cotangent bundle, you can play a little small game, which is taking a Lie group action from the base to the cotangent bundle through this technique called the cotangent lift. And we will see how this cotangent lift is defined. Suppose that you have this action rho, which is a Lie group action on a smooth manifold M. Now, for each element of the group G, there is a natural induced diffeomorphism, which is taking the rho acting by the element G of the group. And then you can take the cotangent lift, you can construct the cotangent lift of this rho sub G that we will call during all the presentation hat rho sub G. So whenever you see a hat rho, it means the cotangent lift of the action. The cotangent lift is defined in the following way. You take an action that will act not only on the base, but on the base plus the fiber, so on the whole cotangent bundle. And this action goes in the in the base manifold, works the same as the original action. So hat rho is simply rho in the base, and it's the differential of rho transpose. So the pullback of the differential of rho and the inverse, finally the inverse of the pullback of the differential of rho is the part of this action acting on the fiber. So the cotangent lift is basically the same action in the base, but on the fiber, you take a differential, you do the pullback, and you invert this action to see what happens in the fiber. This cotangent lift has some super interesting properties that we will see some of them. It's like a really rich tool to deal with physical problems with physical systems, and we will compute some explicit cotangent lift of some action in order to see that it's not difficult to compute in general. As you can see, it's kind of determined by the action on the base, but it offers another approach because, in fact, one of the interesting properties of the cotangent lift is that even that the action is of a compact group, can be of a compact group in the base, when you do the cotangent lift, you are already acting on a manifold which is non-compact, which is the cotangent bundle. So it can generalize results of compact groups on compact manifolds to results of compact groups on non-compact manifolds. So you gain this small improvement of not having to require compactness of the general manifold, which in this case is the this example of the cotangent lift of a group action is the cotangent lift of the rotation of a solid object. If you have a rigid solid, you can consider its rotation by a matrix A of SO3, which you can compute explicitly by simply taking the product A times the position vector Q. And then if you compute the cotangent lift of this action and you take P as the coordinates of the cotangent of the fiber of the cotangent bundle, then you see that this hat rho is simply A times Q, the same in the base, and A times P in the fiber. And if you now compute the moment map of this cotangent lift, you recover the classical Q times P, which is the momentum, angular momentum of this action. So it clearly has applications in physical systems, and what we gain here in the cotangent bundle is that it is a non-compact manifold. So we will be generalizing a result from Palais and from Miranda, which was only valid for compact manifolds, to a non-compact manifold, which is the cotangent bundle of any compact or non-compact manifold. It provides examples of Hamiltonian actions, as in the example we have just seen of the rotation of a rigid solid. It's a transformation. The cotangent leaf is a transformation that preserves the Liouville one form, Amna. So it's a really interesting property, because automatically, if it preserves the Liouville one form, it also, in general, can preserve the symplectic form. If the base manifold was already symplectic, and is a natural leaf from the configuration space, so the position space in a physical problem, to the phase space, which takes into account position and velocity or momentum, if you. So it's a natural setting for physical problems in which you have basically the position and momentum variables. Now, the result I have been typing about is this theorem proved with measuring work with Miranda, in which we prove that if G is a compact Lie group and M is a compact smooth manifold, and then you have two actions, ρ1 and ρ2, which are C1 closed, then their cotangent leaves, so hat ρ1 and hat ρ2, are symplectically equivalent. So they are equivalent via symplectomorphism. So they are conjugated. You can find a diffeomorphism, which is symplectic, so a symplectomorphism that conjugates both actions at the level of the cotangent bundle. That is where both actions, because they are the cotangent leaves of two actions on the base. The proof of this theorem is not really complicated. And first, it needs a proposition. In fact, it needs a definition about, well, we can go directly to the proposition, because we will see the definition in the proof of this proposition. First, we prove that if you have two group actions which are already C1 equivalent, so if you already have a diffeomorphism that conjugates them in the base, then you can automatically find a diffeomorphism acting on the cotangent bundle that conjugates their cotangent leaves with the same C1 equivalency, so at the same level of proximity in the topological sense. You find, I will not take a lot of time in this proof, but you can almost directly find this diffeomorphism, which is basically the cotangent leaf of the original diffeomorphism given by Palais. So Palais already provides the diffeomorphism that conjugates the actions on the base. And if you define the cotangent leaf of this diffeomorphism given by Palais, you find that it satisfies all the properties needed to conjugate the cotangent leaf of both actions on the cotangent. So basically, this hat phi that we define this way. So this hat phi that is defined as phi, the original diffeomorphism on the base, and the inverse of the pullback of the differential of phi on the fiber, in fact, conjugates the cotangent leaf of ρ1. So after proving this small proposition, the proof of the theorem starts by taking this first, the original Palais diffeomorphism that gives the conjugation on the base. Then you take this hat phi that conjugates the cotangent leaves of these actions on the cotangent bundle, and then you have to prove that this hat phi is not only well-defined diffeomorphism, which we already know that it is, but it is symplectic. So it is a symplectic homomorphism. So we have to see that it preserves the symplectic form, which is true, since the symplectic form is a differential of the Liouville one form, and in this case, the pullback and the differential do commute. So this diffeomorphism of the cotangent bundle, apart from conjugating both actions, preserves the symplectic form. So we can say that this action is rigid, or in other words, that ρ1 and ρ2 have cotangent leaves which are symplectically equivalent. Now, the application of this theorem goes to the field of integrable systems, and to give a brief introduction to integrable systems, which has already been done in many of the talks of this Congress. Just say that they come from dynamical systems, which are transformations of the coordinates in some space. They come normally from Lie group actions, because we normally study with tools of symplectic geometry continuous dynamical systems, not discrete dynamical systems. And there are really classical results which already say which is the shape, which is the aspect, which is the structure of a dynamical system, of an integral system in the regular points. So the regular points are well known by Liouville theorem. You also know what happens when you perturb a little bit these regular fibers, the regular fibers you have in the regular points, which is Km theory, which is what happens with the irregular tori when you perturb a little bit systems. But we don't have as much results in the case of the singular points of integrable systems. So when you encounter singularities, you have to apply more sophisticated techniques, some other theorems, which are already, and nowadays we would say that are already classical, not theorems for non-degenerate singularities, but these are the most simple singularities we will see. Sorry, and there are still lag theorems on degenerate singularities, which are the more difficult types of singularities to study in an integrable system. We know that apart from the classical Liouville, Liouville minor theorem, we have a restated version due to the Olympic champion Kissenhofer and Eva Miranda, which says that semi-locally in a regular Liouville torus, the system, the whole integrable system, is equivalent to a neighborhood of the zero section of the general Cotangent model of the torus, the Tn torus. So you can think that in a regular leaf, in a regular fiber, you have a Cotangent model, which is the classical canonical Cotangent model. So it's kind of another way of seeing the Liouville minor theorem, when we will use this in a proof later, in a proof of a theorem in integrable systems later. And now we'll have to talk about singularities. I've been presenting singularities, and singularity is simply a singular point of an integrable Hamiltonian system. So it's a point in which the moment map has less rank than the dimension, half the dimension n of the manifold. And as singular points, you can have super difficult points to study, but the simplest singular points are the non-degenerate points, in which I think the Hessian doesn't vanish, or simply they are the points in which you control more of the first derivatives. You know more information because they do not vanish. In these singularities, in the non-degenerate singularities, there exists a classification which is also really classical now, which is a Williamson classification of these singularities, which we call non-degenerate singularities because they are the simplest ones. And basically, Williamson's theorem says that they can have three forms. The elliptic, they can be of elliptic type, they can be of hyperbolic type, or they can be of focus type. For the singularities of elliptic type, you can find coordinates in which the singularity writes as x squared plus y squared. For the hyperbolic type, you can find coordinates in which the singularity writes as x times y, or as x squared minus y squared, which is the same, which has the same shape basically. And for the focus singularity, which is the special of these three singularities, you can only find it in manifolds which are of dimension at least 4, because it involves the combination of 4 different dimensions, for different coordinates, for different variables. And focus singularity needs 2 components of the moment map to be described, and needs 4 coordinates, and is described through this system of two moment map components, which is here in purple, which is x, which is the shape you have, the form you have. So they are basically, these are the 3 basic singularities you can find in integrable systems, which are non-degenerate. And we can see that we find these kind of singularities in as we will see in the more simple physical examples of mechanical systems. We already find variations of these singularities, and we will see examples of the theory. Then the next step in the classification of integrable systems was to see that the Williamson type of a point on the singularity not only characterizes the point, so the singular point, but also the singular fiber. This is a theorem, the smooth local linearization theorem due to Eliasson and then reproved and improved by Miranda and Zhong, which says that it's not only the characterized the invariant, if you want to think this way, the invariant here is not only the point, but the Liouville neighborhood, the Liouville foliation in a neighborhood of a singular fiber. And they proved that this neighborhood is locally symplectomorphic to the model Liouville foliation given by any singular point of rank K and this Williamson type. The Williamson type, KE, KH, and KF, basically says in the singular point how many components of each type does this point have. So KA is the number of elliptic components, KA would be the number of hyperbolic components in the singularity, and KF would be the number of focus-focus components, which recall that are of double the dimension respect with the other components, of dimension 4 instead of dimension 2. Then the two theorems we obtain for systems, for interval systems with singularities that come from the first theorem I showed you today are two theorems that I call Theorem A and Theorem B for simplicity, and are applications of the rigidity theorem on the cotangent leaf to the case of interval systems with specific kinds of singularities. The first one, Theorem A, basically says, we will see now in detail, basically says that there's a symplectic equivalence, there is kind of symplectic rigidity in the case of systems with non-degenerate singular elliptic leaves. You have.
Hi, Pau, you've just got a couple of minutes left, okay?
Okay, thank you. So we will. Okay, so since we have only a couple of minutes left, we will skip the proof of the theorems, but I will put, I want to put the focus on Theorem B, which in fact is the most interesting one because it can be applied to systems which have degenerate singularities. It says that on systems which have a special kind of degenerate singular leaves, which have a component that is invariant by an S1 action, you can apply our previous theorem to find to prove rigidity of this degenerate singular leaf, which is kind of more interesting because for degenerate singularities we don't have this general theory that we have and this general classification that we have for non-degenerate singularities. This is Theorem A fully expanded with the proof. I will skip for today this proof, but you can find it in our article with Miranda published in Journal of Geometry and Physics. And this is Theorem B, which is already proved here, but I will skip also the sketch of the proof. And I wanted to show you that we can find these singularities already in some basic, super basic physical examples. For instance, we find the elliptic singularity in the harmonic oscillator. We find the hyperbolic singularity in the simple pendulum, not in the bottom equilibrium, but on the unstable top equilibrium on the simple pendulum. And we find also the focus-focus singularity in the spherical pendulum, not on the bottom equilibrium, which is stable, but on the top equilibrium, which is in this case a focus-focus singularity. I will show you briefly the other way around of this same cotangent leaf setting, which is that you can produce the three types of non-degenerate singularities through cotangent leaves. So the interesting point connecting these physical systems and our theorem on cotangent leaf rigidity, you can connect it with physical problems because you can formulate the three types of non-degenerate singularities as the cotangent leaf of three Lie group actions, which are the three written here. If you compute the cotangent leaf of the first action on the left, you can find the vector field corresponding to the elliptic singularity. If you compute the cotangent leaf of the central action, you find the hyperbolic singularity. And if you compute the cotangent leaf of the right action to find the focus singular. I will not enter in how to compute the examples of and how to compute explicitly these singularities, but in the article you can see that they can be obtained explicitly from these group actions. And I will skip now directly to the symplectic slide, in which I only wanted to say that everything I've talked on up to now is on manifolds which do not have boundary, but all these results can be adapted to be symplectic manifolds, to be manifolds in general and be symplectic manifolds in particular. And this is work in progress with Eva Miranda, since we think that they are really interesting manifolds to consider, as in their talk on Wednesday, she already explained, because they are manifolds which model nicely, which model in a nice way, systems, physical systems that have some kind of boundary, which can be a natural boundary, a supernatural boundary for you will be a position boundary, a border, a wall, or can be a boundaries which you obtain after changing coordinates, or a boundaries on the momentum, on the velocity, that are also a physical boundary. So the manifolds model other kinds of physical problems, instead, for example, in fluid dynamics, for instance, in electromagnetic dynamics. And it will be interesting to have this version of this rigidity results. So to conclude for today, we proved this new theorem, which has applications on integrable systems, and will have applications on B-integrable systems when we have the version proved. And we have been able to obtain a rigidity result for manifolds which are non-compact, which are the Cotangent bundle of some manifold. So in some way we have overcome this compactness requirement, so we can apply it to non-compact manifolds. Since there's well, in the focus case, there's an idea that we have still pending to prove, which is that if rigidity and complexification were compatible in this case, if they commuted in this case, we could prove the rigidity of the focus singularity through our theorems, because the action generating the focus is an S1 times R action, which is not a compact group, which is because R is non-compact. But if we could see this as a complexification, which is true of S1, and we could prove this compatibility of complexification with the rigidity, we could prove rigidity of this focus singularity. Another application of these Cotangent models of theorems we have can be found in geometric quantization, in which we are also working, and in the magnetic context, in the magnetism context. There's also work in progress with Baptiste Coquinot from École Normale, in which we are working in big Cotangent models for particles moving in electromagnetic fields, which maybe you will have news about it on autumn if we are lucky with the proof, if we can work the proof. So this is all for today. Thank you very much, and if you have some questions, please ask me.
Yes, thank you so much, Pau, for the talk. Thank you, Eva, for bringing him in. Does anyone have any questions? I haven't seen anyone raise a hand or anything. Okay, well, you're getting some claps from Athia. All right, well, thank you very much, Pau.